This lecture material was prepared by Dr. Nima Mahadian. Welcome, engineering students. Today, we are diving into the absolute beating heart of modern industrial automation, which is, of course, the Programmable Logic Controller, or PLC. Listen, if you're going to control a massive manufacturing plant, a high-speed assembly line, or a complex robotics cell, you absolutely must speak the language of PLCs. But we aren't just going to sit here and learn basic programming today. No, we are looking at the actual architecture of control. We're going to learn how to design code that is safe, highly modular, and elegantly structured for the real, physical world. So let's quickly run through today's syllabus so you know what to expect. We'll start with logic, modularity, and subcircuits, then move into advanced latch state management. After that, we'll cover timing, specifically pulses versus windows, before tackling sequencing and shift registers. Finally, we'll wrap it all up with synthesis and best practices. All right, let's jump right into Section 1, Logic, Modularity, and Subcircuits. Okay, I want you to imagine a really heavy industrial machine. Let's say it's a massive hydraulic press. Obviously, for safety, that requires multiple redundant operator inputs before it can even activate. We literally can't just rely on one single button here. We need the operators to have their hands completely clear of the danger zone, activating very specific combinations of switches. So how do we actually program this safely? Well, before we even look at the code, let's establish our variables so we're all on the same page. We've got 4 physical sensors out in the field: in 1, in 2, in 3, and in 4. These are all normally open, or NO, operator inputs, which basically means they only pass electrical continuity when someone physically presses them. And then our output is CR1, the motor latch output coil. That's the variable that will actually physically spin up the heavy machinery. Now notice how we translate that physical requirement into modular ladder logic. Just take a look at the code console here. Remember the basic PLC scan cycle, right? The processor reads the inputs, evaluates the logic from left to right, top to bottom, and then updates the outputs. So in this case, we've organized the logic into nested topologies. Subcircuit 1 is an OR block. Basically, if IN1 or IN2 is high, that left side is true. Then subcircuit 2 is another OR block, IN3 or IN4. But pay close attention to how they are wired in series. This essentially acts as a logical AND between those two distinct subcircuits. Let's look at exactly how the PLC executes this in statement list, or STL code, going line by line. Address 0 is load in 1, and address 1 is OR in 2. That right there builds our very first block. Then address 2 is load in 3, and address 3 is OR in 4. That builds our second block. Now address 4 is where the magic happens. The instruction is AND block. This specifically tells the PLC to logically combine the previous 2 nested subcircuits. Only if both of those subcircuits pass continuity will it actually execute address 5, which is out CR1. So, step 1, subcircuit 1 goes high. Step 2, subcircuit 2 goes high. Step 3, the logic block completes and CR1 latches. Simple, right? But I have to issue a really stern engineering warning right here. There is a massive diagnostic trap waiting for you if you get sloppy with this code. If you fail to properly group those OR branches into subcircuits, like say you just forget to type that AND block instruction in your STL, you're going to end up with one massive continuous OR chain. And what happens then? Well, you get an unintended bypass of that second safety condition. An operator could literally just press IN1 and boom, the machine turns on immediately, completely ignoring the IN3 and IN4 safety requirement. Out there in industrial automation, that kind of mistake costs fingers or much, much worse. So please, structure your logic. Moving right along to Section 2, Advanced Latch State Management. So our next industrial challenge is figuring out how to design a start circuit that strictly requires a dual sensor failsafe to halt operation. Basically, we need to conditionally break a safety latch using an intermediate memory bit. Let's look at our intercept variables. IN1 is our start button, which is normally open. CR1 is our primary hold, the motor coil. IN2 and IN3 are our 2 halt sensors out in the field. And crucially, we're introducing AR1, an auxiliary relay. I really want you to specifically note that AR1 is going to act as a normally closed or NC contact, so we can physically intercept and break this circuit. And this diagram brilliantly illustrates that solution. Walk with me through this 3-step state machine on the ladder diagram. On the very top rung, that parallel IN1 and CR1 branch is what establishes the hold. When IN1 goes high, CR1 turns on. And because CR1 is wired in parallel with IN1, even when you let go of that start button, CR1 keeps itself latched on. But now look at the second rung. IN2 and IN3 are wired in series. This branch strictly requires both of those secondary conditions to be true in order to trigger the AR1 auxiliary relay. Once IN2 and IN3 go high, AR1 energizes. Now look back up at that top rung. You'll see an AR1 contact wired in series, but it's a normally closed contact. You can tell by the line drawn through it. In our STL code, this is address 2, and not AR1. Because it's normally closed, it happily allows power to flow while AR1 is off. But the very split second AR1 energizes down in step 2, this normally closed contact in step 3 violently opens up. That physically breaks the CR1 latch and safely halts the machine. Here is another fatal diagnostic trap that catches so many people. What do you think happens if you accidentally use a normally open contact for AR1 in that primary rung instead of a normally closed one? Just think about the engineering physics of the circuit for a second. If it's normally open, power simply cannot pass through it until AR1 is energized, which means your IN1 start button would do absolutely nothing at all. That fatal error prevents the circuit from ever starting in the first place. You absolutely must explicitly understand the difference between NO and NC contacts when you're designing intercepts. Now, what if we want to break a latch based on a specific sequence of events, rather than just relying on sensors? Consider an industrial batch processing workflow. Maybe it's a stamping press that has to stroke exactly 3 times and then completely stop. We can actually achieve this precise operational loop by using a discrete event counter, just like you see here. Let's look at the logic flow. Step 1, the operator presses IN1. That initiates the CR1 latch to start up the press, and simultaneously, down on a parallel rung, it resets counter 1, or C1, back to 0. Step 2, every single time the press completes a stroke, sensor IN2 sends a pulse. Those successive IN2 pulses physically increment counter C1. Then, step 3, C1 reaches our predefined constant of 3. So what happens? Look at the top rung again. Notice there is a normally closed C1 contact right smack in the middle of our CR1 latch. When that counter hits 3, the NCC1 contact instantly opens up and CR1 terminates. But beware the trap here. If you forget to program the counter reset logic, meaning if you forget to map IN1 to reset C1, you've just built a one-time use circuit that will permanently lock you out after the very first 3 events. Okay, section 3. Timing. Pulses versus windows. As engineers, we are constantly needing to delay the start or delay the end of a physical machine action. But how do we actually manipulate time within a PLC scan cycle? Well, here we have 2 fundamental engineering mechanisms sitting side by side, generating a pulse versus sustaining a window. Over on the left, we are generating a pulse to delay the start of a machine action. This requires continuous input to accumulate the time. The mechanism here actually relies on 2 timers fighting each other in sequence. When IN1 is held down, T1 starts accumulating. Then T1 turns on T2, and then T2's normally closed contact immediately kills T1. It's this cyclical fight that ultimately results in a delayed start. But on the right, we have a vastly cleaner architecture for delaying the end of an action, which is sustaining a window. This only requires a momentary input, just a single button press. IN1 triggers a self-sealing latch on CR1. CR1 then turns on timer T1. When T1 hits its 5-second constant, its normally closed contact on the top rung opens, and that self-sealing latch is violently broken by a single timer. So, one delays the start, the other delays the end. You really need to choose your architecture wisely based on the physical mechanics you're trying to control. That brings us to section 4, sequencing and shift registers. So, industrial processes are rarely just singular actions, right? Think of a bottle assembly line. A bottle has to be filled, then capped, then moved down the line. Each action has to occur sequentially, handing off control to the very next step. And this introduces us to what we call the cascade problem. At first glance, sequential logic just looks like a tangled web of dependencies. It's a brute force temporal model. Our challenge here is coordinating 3 distinct 5-second operations, CR1, CR2, and CR3, and making them trigger one after another automatically to form an infinite loop. If we try to do this just using timers, we literally need a separate rung and a separate timer for every single step. In1 and the absence of T1 starts CR1 and T1. Then T1's completion starts CR2 and T2. Then T2 starts CR3 and T3. It's this wildly complex, interconnected chain of normally closed and normally open dependencies. If even one timer fails, your whole entire line jams up. It's rigid, it's dense, and honestly, it is a total nightmare to try and troubleshoot at 3 a.m. on a factory floor. So, the crucial point I want to make is there is a vastly better way. Instead of relying on time, we rely on events and memory to build an elegant solution using shift register control. Check out the sequence state machine. Just look at the memory map visualization. A shift register allows a single binary bit, just a 1, to physically move through memory addresses. It goes from AR0 to AR1 to AR2 to AR3. And it's driven by a clock pulse, which in this specific case is the rising edge of sensor IN2. Let's look at the STL together. Address 0 to 3 sets up our shift instruction. Load in 2, shift AR0. Every single time IN2 triggers, whatever data is sitting in AR0 gets pushed down the line. Step 1. IN1 primes the register, latching AR0. Step 2. The IN2 rising edge physically shifts that bit from AR0 down to AR1, which turns on our first output, CR1. Step 3. Subsequent IN2 edges shift the bit down to AR2, and then AR3. Finally, Step 4. Sensor IN3 acts as a global reset, dropping the whole thing back to 0. It's clean, it's linear, and it is highly efficient.
Wait, before we move on, we have to talk about the engineering rationale behind a very specific piece of logic here, the AR10 one-shot. In that STL, you'll see out AR10 right after the shift. If you fail to include this one-shot logic constraint, you are going to cause a catastrophe. Why? Because a PLC scans its logic hundreds of times per second. So if an operator sustains a press on that IN2 button, the PLC is going to read that input as high for dozens of scan cycles. Without the one-shot explicitly constraining the shift to a single step per event, that bit will instantly race through all the registers in a matter of milliseconds. Your entire assembly line process will trigger almost simultaneously, and it'll be a mess.
Finally, Section 5, Synthesis and Best Practices. Look, as engineering students, you aren't just learning how to write lines of code, you are learning how to make high-level architectural decisions. You really have to know why you're choosing one method over another out in the field. So let's compare those brute force cascaded timers directly to the elegant shift registers. First up, scalability. Cascaded timers, pretty poor. You need completely new rungs and new timers for every added step. Shift registers, excellent scalability. You simply expand the target register length. Second, instruction count and memory usage. Timers are high. We're talking 23 dense instruction lines just to get 3 steps done. Shift registers are highly compact, only 18 instruction lines covering 4 steps. Third, ease of troubleshooting. Finding a fault in a massively complex, interconnected timer chain is really difficult, but with a shift register, it is incredibly simple. You just monitor the exact bit location in the memory map instantly. And finally, temporal control. Cascaded timers force you into a time-driven sequence with fixed, rigid durations. Shift registers, on the other hand, give you a flexible, event-driven sequence that actually adapts to the real physical mechanics of the machine.
I want to leave you all with this core architectural insight from the lecture. Shift registers fundamentally decouple the sequence logic from the timing and event logic. This right here is the true secret to advanced PLC programming. By separating what happens next from when it happens, you're creating cleaner, safer code for physical machines. You get to move away from a brittle, time-driven brute force model, and you elevate your designs into elegant, event-driven state machines. So as you head out into the industrial world, ask yourself, will you build rigid time traps, or will you engineer intelligent architectures? The choice is entirely yours. Thank you for joining me for this explainer, and keep coding safely.